Hello and welcome to lesson 14, where now we're getting familiarized with another rule for differentiation, and that's our product rule. So today you're going to be learning how to differentiate products of functions using the product rule. So to start, consider first the function f of x, which is x squared plus 2, and g of x, which is x plus 5. And let p of x be f of x times g of x. And we're asked to show that the derivative of p of x is not the derivative of f of x times the derivative of g of x, which is maybe what you were expecting when you saw sum and difference rule, but it is actually not the case for product rule. So we're going to show that. So we're going to start by just expanding p of x. So knowing that we have those the product, so this product here, x squared plus 2 times x plus 5, we're going to expand it. And if you remember from last class where we had, for example, f of x is x plus 2 squared, I told you you cannot just apply the product rule here. And what we had to do, and keep in mind, this is just x plus 2 times x plus 2, right? We had to expand this and apply the sum rule for each of the terms because the product rule didn't work. And here we're also going to see that this version of the product rule does not work for derivatives. So now, expanding this here, we're left with x cubed plus 5x squared plus 2x plus 10. Now, finding the derivative here, and I'm just applying the sum rule, the product rule, and the constant multiple rule. So for this first part, we have the product rule, which gives me 3x squared. In the second part, I left the 5 and then x squared. So dx squared dx is 2x by the power rule, and this times 5 is 10x. And 2x is going to be the constant multiple rule. We take the 2 out, and then dx by dx is just 1. And finally, that 10 is just a constant, so the derivative is just 0. So this is what we expect our derivative to be. Now, let's find the derivative of f of x, which is going to be 2x. So this is just the power rule for x squared, and the 2 is a constant, so it just becomes 0. Now, g of x is x plus 5. So again, by the derivative rules, I'm first applying the sum rule. So d of x is just 1, and the d of 5 by d of x is 0. So this is just 0 by the constant rule. So then, p prime of x, which we found from above, is 3x squared plus 10x plus 2, is not equal to the product of those two, which is 2x times 1. We can see those are very completely different equations. So that's why it doesn't work, and we can't apply the product rule that way. So let's see what the product rule now actually is. So the product rule tells us that, again, we have that function p of x, which is equal to f of x times g of x. Then the derivative is going to be this expression here, which is the derivative of the first function, so f prime of x, times just the second function itself, so g of x. We're not doing anything to it. And this is going to be added to now, again, in this one, we're just keeping f of x, we're not changing it, but now the prime or the derivative of the second function, so g prime of x. And in Leibniz notation, if u and v are functions of x, then d of uv, and this is just a product, u times v, of d of x is going to be the derivative of u by with respect to x, or du by dx, times v, I'm not changing v, and in the second term, so we're adding these two terms, we have u times the derivative of v with respect to x, or dv by dx. Now, the proof of this, so we start with p prime of x, and we're taking that limit, so the definition of the derivative. So here we're going to have f of x plus h times g of x plus h, because that's what p of x is. It's the product of f of x and g of x. And in the second part, that's all we have. This is just p of x, and this part is p of x plus h. Okay, and this is just, again, for this part, substituting x plus h here, I would just end up with f of x plus h times g of x plus h. Now, to evaluate this limit, we're going to do one part here, which is add and subtract this term. And if I add plus 2 minus 2, this is just 0. I'm not actually changing my expression. But similar to rationalizing numerators or denominators, we want to do perform an action here that's going to help us rearrange this. So keep in mind, this is the same term, just subtracted and added. So this is actually just 0. But now, I'm going to split this into two fractions. So in the first part, I'm going to have f of x plus h, g of x plus h, and the subtraction piece. And in the second part, I have f of x times g of x plus h, and the my last term, I'm just keeping it the same. But now, I have a g of x plus h in common in both of these. And I can factor that out. And in this one, I have an f of x in common that I'm going to factor out. And now, applying my sum and product rule for limits. So this is just, in this example here, this is a constant. And the product rule for limits tells me that I can separate this and this term, and limit of h approaches 0 of g of x plus h is just going to be g of x. And again, I could factor that out, and I'll be left with this limit here and this limit here. And this is just my, I'll just show you, this is the two pieces here. This is the g of x plus h, and this is the f of x. And now, by definition, this is the derivative of f of x. And this is the derivative of g of x. And this one, again, like I just said above, this is just g of x. And this one doesn't even have any h, so it's just f of x. And that's exactly the product rule that we just saw. Now let's see it in a worked example. So here you're given 2x minus 1 times x cubed minus 3x. So this is a product, and in this case, we might have, just so you see with the different function notations, this would be 2x minus 1 and x cubed minus 3x. Oh, and that's exactly right there. And now, f of x is the product of p of x and q of x. Then the product rule is going to tell us that f prime of x, or the derivative of f of x, is going to be this expression right here. So let's work piece by piece. We're going to find the derivative of each of those. So p prime first, or derivative of p, is going to be 2. The reason for that is the negative 1 is just a constant, it'll be 0, and 2x, the derivative by now we know is 2. Now, q of x, the derivative is going to be, the first part is 3x squared by the product rule, and this is a difference, the difference rule, so negative 3, and the 3 is just because negative 3x, or 3x, would just be 3. Because d of x by d of x is 1. Now, we're just going to substitute those values in. And keep in mind, this is my q of x. This is p of x. And so, in each of these two terms, I need the q of x and the p of x, but one of them is going to be the derivative. So here I have p of x. So this one is going to be the derivative, and in this one, it's going to be the derivative there. And so now I'll just substitute those values. We have 2 here, and in this one we have 3x squared minus 3. And now we're going to expand this to show that it will actually equal this derivative right here. So f prime of x, we have 2x cubed minus 6x plus 6x cubed mine plus 3 minus 6x and minus 3x squared. Okay, and let's see, these two will be 8x cubed. Here we have just a negative 3x squared and negative 12x and 3. And that's exactly what we were looking for. So yes, the product rule worked, and that's what we got. And if you're still not sure, you can expand this, and maybe we can try that too. So if we expand this, I have 2x to the 4 and minus 6x squared minus x cubed and plus 3x. Okay, and let me just bring this down. And one thing I'm going to do is I'm just going to rearrange this to have my degrees in order. But it's the same thing, right? With addition and subtraction, we can do that. Okay, there we go. Now, this I'm going to find by the sum and product rule, the derivative. So f prime of x. So here we have by the product rule, we get 8x to the power of 3. In the next one, we get negative 3x squared, negative 12x plus 3. And you can see that these two are the same thing. So regardless of which way you try, the derivative is the same. But you'll see later on when we have more complex functions, it's good to know the product rule because sometimes we don't want to be expanding and then finding the derivative. So yes, but either way, whichever method you try, we get the same answer. So here, I gave you another problem just to try on your own, just to make sure you fully understand product rule. So for this function h of x, it's the product of these two functions. So you can try now either expand it first and then find the derivative, or use the product rule, or actually do both and then compare, and you should get the same answer for both. But definitely try the product rule to make sure you fully understand that. Now, our next example, we're told to find the value of h prime of negative 1 for the function h of x. So this is just asking to find the slope of the derivative, or sorry, the slope of the tangent at x is negative 1. So let me write that. Slope of tangent at x is equal to negative 1. And what I want to show you here is that regardless of how many terms are in your bracket, the product rule will still hold. Because keep in mind, it was the product rule is just f of x is p of x and times q of x. And p of x and q of x can be any function. As long as they're differentiable, then you can apply the product rule. So here, in the first part, let's put this one as do p of x and then q of x. So first, I'm just going to, as a rule, just always like set up your derivative. So here we have q of x and p of x. So then this one is going to be the derivative of P, and the derivative of Q. And we can now check. So given P of X here, let me just write that here too. Using the product rule and, or sorry, the power rule and the sum rule, we get 15x squared. Here we get 14x, and here this is a constant, so just 0. And that's exactly what I have there. Now for Q, we have this 2 is our constant, so we just have 4x, and this one is just 1, and the 6th constant is just 0, so 4x plus 1. And now one thing here, because we're asked to find the derivative at -1, you don't actually need to expand this whole thing. As I'm sure you can see, it's a very complicated task to expand this. So what I did is, and I'll update this here for you. This should say just -1. Or let me just rewrite that. It should be h prime of -1, same here. Because I'm just going to substitute -1 there and just start solving, because that's what I really want from this question, right? It's good to have this derivative function, but for the sake of this question, I'm just going to start solving to make my life easier. So I'm just putting -1 wherever I had x, and you can see that this simplified will eventually give you -8. So please make sure you check through all those steps and know how to work with simplifying this expression. And if you remember in our prerequisite skills, we did have simplifying expressions because exactly like this example, you get to more complex equations and expressions where you need to simplify. So it's good to have that skill and practice. So just to generalize this now, the product rule with can have more than 2 terms as well. So given, I'm going to show you the one for 3 terms, for example. Given P of X is f of x times g of x times h of x for 3 functions, f of x, g of x, h of x. And again, keep in mind, these are all differentiable. These 3 are differentiable functions. Then the product rule is, and take a look and see if you notice the pattern here. So I'm going to maybe start highlighting for you. So you're pretty much taking the derivative um, of, for example, the first function here. The other 2 stay the same. Then in the second term, you take the derivative of your second function, and the other 2 stay the same. And then finally, you take the derivative of the last function, and the other 2 stay the same. And same with Leibniz notation. You have, if you have UVW, this will become U prime, and then VW plus U, and then here we have the V prime times W, and finally the W prime, and then U and V just stay the same. Now, the proof of this actually comes from the product rule itself. So we're going to group this so that the first 2 terms are together. So we have f of x and g of x. This is one function itself. And you're multiplying this by h of x. So the product rule tells us that the derivative of p of x is going to be the derivative of this bracket here times h of x plus that bracket itself times the derivative of h of x. But then this itself is a product. So we have to apply the product rule again, which gives us f prime of x, g of x plus f of x, g prime of x. And this was multiplied by that h of x to begin with. And over here, we just have f of x times g of x times h prime of x, which this is actually our last term here. And now we get the other 2 terms from expanding this, and this is exactly our product rule. And just as an extension piece, you can try writing, I have to think of more letters. So if we have maybe I'll do it. If you have P of X is F of X times G of X times H of X times, um, uh, let's do maybe S of X. There we go. Then what would the product rule look like here? So what would the derivative of P of X be here? And there is actually a pattern, as I'm sure you saw already. So here you're just practicing applying the pattern to see what you would get. And as a hint, your final answer should have four terms. So four terms added together. Now, here we are given y equals x times x squared minus 4 times x minus 3, and we're asked to find the derivative in simplified form. So here we're just applying the product rule for the three terms. So we're just practicing the product rule for a function with three products. So the first function being, maybe let me highlight again, x, and then we have x squared minus 4, or, and then this one, and then x minus 3. Okay, so you can see that each function is appearing in each term, but the first one we have the derivative of x, and this one we have the derivative of the second term, and finally we have the derivative of the last term. And I just rearranged them a little, but with multiplication, the order does not matter. So now let's find those derivatives. So the first one, we know this is x. This one would be 2x, and the minus 4 is just 0. And then finally, we have x here. Or sorry, we have 1 here, because the x would just be 1, and then negative 3 is a constant. So now let's try to expand and check that this is equal to the expression there. So dy dx, and this is f prime of x, is x squared minus 4, x minus 3, and this is just 1. And then we have x minus 3, and then 2x. And for our last term, we have x squared minus 4, and 1. And now this will become um, okay, and finally we have x cubed minus 4. Okay, and let's collect all our like terms and see if those two match. So we have 4x cubed minus 9x squared. Oh, this one should be a 4x, sorry. And minus 8x, there we go. And then finally our 12, okay? And there we go. We have these two matching, and exactly, that's our derivative for product rule with three terms, or when we have three functions and multiplying them, we can find the derivative rule or the derivative function using the product rule, similar to this. So now, how can you use the product rule to find the derivative of a cubic function, such as f of x is equal to x squared minus 3? So this is just like I told you with the squared function. This is x squared minus 3 times x squared minus 3 times x squared minus 3, right? So exactly like here. And so our g of x, which is going to be x squared minus 3, then we actually have f of x is equal to g of x times g of x times g of x. And this is actually, when you do the product rule with three terms, you're going to see that it's the derivative of g of x, so g prime of x, and then the other two terms are just g of x two times, so g of x squared. And so this term is actually repeating three times. So this is 3 times g of x squared times the derivative of g prime of x. And g prime of x is just or the derivative of g of x is 2x. Because of x squared minus 3, we get 2x, and the 3 is just 0. And so the derivative of f of x is now 3, which is the 3 from here, just g of x itself squared, and then the 2x there. And if we simplify, we get 6x times x squared minus 3 squared. And I want you to consider now, what if you have a function f of x is equal to g of x to the power of n for n greater than 3? And so, for example, consider n is equal to 4, 5, or 6. And what would the derivative, so f of x, would be like? And is there a generalized rule there that we can follow? And that is actually our power of a function rule for integers. And if you remember when we did with when we had the squared function, I told you we're going to see a rule from it later on, and this is exactly that rule. So it's when you have a function and it's raised to a power, and it has to be an integer power here now, then we have a rule for finding the derivative. So consider f of x is equal to g of x to the power of n. Then the derivative of f of x is, and this is now actually that our power rule there, right? If you remember, it's n, so our power is now the coefficient. G of x now, n minus 1, and then we have g prime of x, or the derivative of g of x. And in Leibniz notation, if we have a function u that is a function of x, then n is an integer, then if we have u to the power of n, the derivative of this can be found as n times u to the power of n minus 1, and this is now just the same as g of x, right? Or g prime of x. It's the derivative of u with respect to x. So let's try that now. We have our function h of x, which is x squared plus 3x plus 5 to the power of 6. So this tells me that h prime of x is going to be, first I'm going to put my power there, 6, x squared plus 3x plus 5, and this is 6 minus 1, which will be 5. And then we find the derivative of that bracket here, which now you should be more familiar with our derivative rules. We are left with 2x plus 3. And here I'm just going to rewrite that a little nicer, just to have that 5 in there. And that's pretty much it. That's all we had to do, okay? And for example, if I add in this g of x here, this is g of x, then this is g prime of x, or the derivative of g of x. Now you're asked to show that this function here has a derivative of f prime of x is equal to negative 17 over 3x minus 1 squared. So I've already done this for you before when we were working with power rule, but 3x minus 1 in our denominator is actually 3x minus 1 to the power of negative 1. And that's just our exponent rule there. So then f of x is actually 2x plus 5 times 3x minus 1 to the power of negative 1. Now I'm going to use a mix of product and power rule here, or a power of function rule. And yeah, actually, one thing I'll highlight here, power rule and power of a function rule are different. So please make sure when you're naming them, you correctly identify if it's a function raised to the power, it's power of function rule. But if you just have For example, x to the power of n, this is power rule. Okay, so the base makes the difference. Now here, I start with the product rule. So first thing, I'm just writing this second part. So let me get back to highlighting. So then this one is, and then here we have this and here. Okay, so this is just the derivative of 2x plus 5, which by sum rule and constant multiple rule, we know it's just 2. And then we just multiply by the second function, which is 3x minus 1 to the power of negative 1. In the second term, I write 2x plus 5, and now I need to find the derivative of this, which is now the product of a function, or power of a function rule. And negative 1 is an integer, so I can work with it. It's even though it's a negative, it still follows the rule. So here's the negative 1, and then 3x minus 1, and now this is just negative 1 minus 1, right? And then we find the derivative of 3x minus 1. So now let's try this. So here I have 2, and this is really 3x minus 1. And then plus here. So this is just 3 by difference rule as well as the constant multiple rule. So then I just have, or actually perhaps negative because of that negative there, and I'm left with 6x plus 5, or plus 15. And I just multiplied the 3 by the 2x plus 5, or you don't have to, you can just leave it as 3 times 2x plus 5. And now we have this over 3x minus 1 squared. And you can leave this as what we have right now, but if you want to go an extra step, we can write this as 3x minus 1 minus 3 plus 5 over 3x minus 1 squared. And let's do one more step here. We're going to have 6x minus 2 minus 6x minus 15. And this will be over 3x minus 1 squared. And finally, that actually is a little bit nicer. We have, oh, and actually we had to do this because, remember, we were asked to show that this equals to this value over here. And if you didn't expand it, and if you left it here, we wouldn't have that. But we had to go this extra step, and now we actually see that's a pretty nice expression there, and it equals to the expression we were looking for. So our work is complete. And like I mentioned, now we have our rules of differentiability. So power rule is there, sum and difference rule is there, and now we have product rule and power of a function rule added in here as well. And that's a wrap on our lesson for today. So you have some practice questions there, and you can check Google Classroom for any additional tasks. And as always, if you have any questions, please don't hesitate to reach out, and I'll see you all next class.